let's do the distributive property, but geometrically. So as you can see here, we have two binomials, and they just so happen to be the same. Now let's let this first binomial be equal to the side length, this side length in particular, of this shape. So this side length is x plus y. Let's do the same thing down here for the second binomial. Let's make this equal to x plus y. Now, as you can see, x plus y is the same as x plus y. So this shape right here is actually a square. Alright, so here we know a portion of this side length. We don't know exactly what it is, but a portion of the side length is x, and a portion of the side length is y. So I'm just gonna draw a line. Now we don't exactly know what it is. Like this side length could be x, side length could be y, it could be the other way around. This could be y, this could be x, or it could be slimmer, shorter. We don't exactly know what x is, what y is. So this is not drawing to scale. Keep that in mind. Alright, so now that we've divided it, we can see, suppose that this side length is x, suppose this is y. Let's do the same thing for this side length right here. Let's draw a line. And let's suppose that this side length is also x, this one is y. Now we have this square separated into 4 different shapes. And we can actually calculate the area of each shape. So let's go ahead and do that. Here we know the side length is x for this large piece. So we know that one side length is x, the other one is x. So it is x times x, that's the area. Or it's just x squared. If you think about it, x to the 1 times x to the 1. These have the same base. So you can add their exponents. So it would be x to the 1 plus 1, which is really just x squared. Alright, so we know that this area right here is x squared. Alright, that's the area. Now let's calculate the area of this quadrant. So we know one side length is y, as you can see here, and one side length is x. So the area of this would be x times y, or just xy. You could also write it as yx, since the order in which you multiply doesn't matter. Now let's look at this shape right here. We know one side length is y, and this side length is x. As you can see here, it's x. So it'll be the same answer as this, since we're multiplying. X times y. Now for the last one, this side length is y, as you can see from here. This side length down here is also y. So we're multiplying y by y, which is just y squared. Alright, so now we've calculated the area of each section of this square. But what if we added all of these together? Well, that would give us the total area of this square. So if we add each area, so let's focus on x times x and x times y. So referring to this section of the square, if we were to add x squared, this area, with xy, then as you can see here, we would know the total area of this section, the one that I'm outlining. So if we were to add all of these, then we get the total area of this square. So let's go ahead and do that. We have x squared plus xy plus xy plus y squared. Now we can't simplify x squared any further since there aren't any terms with base x to the power of 2. Same thing applies to y squared. As you may have noticed, this right here, these two terms are the same. So we'll have x squared plus 2xy plus y squared. And that is the total area of this square. And we also know that the area of this square is x plus y times x plus y, because we have each side length equal to x plus y, x plus y. So this is how you would distribute geometrically. Now to verify our solution, you can notice that x plus y times x plus y is actually a special case of factoring quadratics. This right here is a perfect square trinomial. So if something takes the form of a plus b times a plus b, it's really just equal to a plus b squared. That'll be a squared plus 2ab plus b squared. As you can see, this right here is the same form as this. So we know that our answer is correct.